So a lack of EMC is what we call EMI, interference, where emission is too high and or immunity is too low, or susceptibility, that's actually where things go wrong. So the device is susceptible to noise. So at this frequency we can expect, well, we'll see a negative margin and we can expect some interference. So if you stick to the standard, it should be fine. Should. So in a minute I will show you some demos with power electronics. So I've got the variable speed drive, a circuit breaker, radio frequency transmitter, some victims, some devices that are sensitive, to show you some coupling paths, some cable shielding. And, well, let's start with this one. I've got my transmitter here. And when I push the key, and I've got my temperature sensor here, then actually I'm producing an EMI problem now, because my temperature, for the ones with the good eyes here, is the this one, so 23 degrees centigrade. And I push the key, it goes to 14, 102, minus everything you want. And I actually get an alarm on my system. Well, this is not a critical measurement of temperature, but if it would be pressure or something controlling your car, then it's not good. So what happens? An idea. I've got fields, cable. The cable, right. So this is the first learning point. If I don't have a cable, there's probably not an issue. So actually the field is going to induce some current, some noise current on the cable, which is going to the sensor, sorry, to the PLC of the analog electronics. And there it's going to produce an offset in the working point of the transistor. It's going out of the limit that I've set in the frequency. So if we look at the specifications, so let's find out what goes wrong. We've got the specification of the PLC that says it has been tested to this standard against 10 volts per meter. So I'm curious what comes out here. So I've got my more or less scientific field strength meter, and when I push the button, then when it's going to the red level, then it's actually 10 volts per meter. If it's yellow, it's 3 volts per meter, but actually I'm producing quite some field here. So this is not, well, close or even above the limit where it is tested to. So this is what we expect. And there's another thing, that if I look at page, well, let's say page 70, somewhere in the back of the manual, then I can see that I have to use a screen for the sensor. Whereas I didn't read the manual, I just used a plastic lamp and unshielded cable. That's probably the big difference. So there are two issues: specification of the device and cabling, quality of the cable. Well, a few words on the necessity of the margin. We may have lots of equipment in the same installation. So, for instance, this variable speed drives. So these are motor controllers in a beer brewery. So you've got all the belts with all the bottles, lots of motors, and they are controlled by these variable speed drives. So lots of them. And each has a certain emission level, and well, of course, some 80 of the drives will have more emission than this one. So that's why you need some margin. There's also some gaps in the standards. So we're not going to tell more about standards, but the standards are not perfect. So not complete frequency range or the wrong level or whatever. This is an example. So you may even see a warning in the manual that you use a product standard, and this may cause radio interference in the domestic environment, in which case you have to take supplementary mitigation measures if required. So you actually buy the device and get the warning with it. And then you have to find out yourself. Different environments. Your car is going to be almost everywhere. It's going to be in the garage, in the residential area, it's going to the motorway, it's going in the jungle, it's going everywhere. Even near transmitters, also lots of mobile phones. So it's a rather harsh environment for a car. Different installation practices, so the perception of EMC for different installation companies is quite different. Huge differences in cabling practices throughout the world. So things can look very nasty with lots of wiring. We have to find out about the screens, whether they are connected or not. Some warning about screen cables. But again, a very high margin is expensive. So we have to find the optimum balance of all these things and the money we spend on them. Well, a list of frequency experience sources, power electronics. It's going to be used in your electrical car. So you've got a drive, electronic drive for the motor. But also in buildings, it's a lighting system with the ballasts. Switch power supply things, UPS systems, circuit breakers, lightning. I think there's also a movie about the lightning hitting a car. Yeah. And it's not a problem. It's really fine. Metal car now. A metal car, sorry. A Faraday car. Transmitters, ESD. You can explain a little bit about ESD. And some continuous and transient sources. Transients are quite difficult to find something, what's going actually happening. Because continuous, when you switch on, it's there. You can find out. But when it's transient, you have to find out which moment when it goes together with another thing. So you need some more measurements very often to find out. But continuous is again the converter, servo drive, UPS, switch mode power supply, transient, relay valves, ESD lighting.
A little bit. Okay. Oh, okay. Back to the basics. Some theory, a little bit theory. Kirchhoff's electrical law. Everybody knows it, I hope. You use it to calculate the lights and the battery and the currents and so on. So it's very common in electronic engineering. It tells you that the sum of currents going on a set of conductors which are connected should be zero. So everything going in has to go up. It's not left behind somewhere, so no charging or so. If you transport that to a single wire, one wire, it means that the current coming in here at this point has to go out. And then if that was it.
That's long enough.
You charge it, yeah, nice. Okay, current going in has to come out, and that essentially means that anything going here has to go back. Unless there's a bucket of charge here and another one here feeding it. So if it's not there, everything going in must come out. So every current must have a return path, which is very essential. Also comes for